Hi people, welcome back to the next lesson on stress and strain. I didn't mention it earlier. In stress and strain, there's sort of two parts. Okay, in the first part, we looked at members which was made up of one material only, meaning it's like a steel bar, it's the mild steel bar, it's a high yield steel bar. It's a timber beam, it's a concrete column, etc. Okay, but in the second part, we're going to look at, yes, I think you've worked it out, you've guessed it, we're going to look at something like, for example, like a reinforced concrete column, which has two types of materials working together to resist loads. Okay, for example, like a square column might have 4 or 6 steel bars in it, is undergoing a compressive load. We're going to work out the stresses and strains related to materials that are working together. Okay, so that's the second part of stress and strain. And if I go back to the notes, which is on Blackboard in the core notes, I am going to page 2.8. That means chapter 2, page 8 in chapter 2, and I'm reading from it. It's called compound bars. Okay, compound just means something made up of many. I'll just read through some bits, explain some bits as I go along, and do some worked examples again. Okay, compound bars, members made up of two or more components of different materials and constructed in such a way that the components deform equally. Very important word there. Okay, that means they held together. Like for example, if you take like say a concrete beam or concrete column, okay, the steel is first placed in there inside the formwork, the concrete is poured, and the bars have a rough out texture. Okay, the bars have a rough texture. Maybe I'm gonna see if I can dig at the picture quickly. Okay, I've dug at the picture quickly. The famous old Google. Okay, people, there's many pictures there, but let's look at this one here. Okay, the bars have a rough texture. Okay, there's bars, rebars. It's called rebars. It's a short word for reinforcing bar. Okay, why do you think the texture is rough? Yeah, so that as the concrete sets and hardens, it sits all between these little edges, these raised edges. Okay, so as the concrete dries and it gets hard, it actually holds tightly onto the bar. Okay, so as the column or the beam wants to bend, and if the concrete was unable to hold on to the bar will just slip inside. It will move freely inside the concrete. Okay, so we have rough bars there, so the concrete holds onto it, and that is how the two act together. Okay, and by the way, that word there we call bonding. Bonding, B-O-N-D-I-N-G. B-O-N-D-I-N-G. I don't write here. The word is bonding. Yeah, where am I now? There we go. Yeah, yes, let me write it. Bonding, just quickly. Okay, that's when the concrete bonds with the steel. That means as it hardens, it holds onto the bar. So the steel and the concrete almost become one. They bond with each other. Okay, so if I'm flicking back to our note here, it says that the components deform equally under axial loading are called compound bars. Okay, so consider the beam shown below. Now the beam might look like two plates, but okay, let's consider a structure which is made up of two materials which is bound together. Okay, so that they flex and work and they twist and they shorten and they lengthen by the same amount under the load. Okay, they have to do it by the same amount because remember, they are kept together. Consider the bar shown below made up of two components, one of material A and the other material B. It could be steel and concrete. Okay, the two components are secured together along their length so that they remain of equal length when the load F or P, if that P is the same thing, is varied. Okay, right. So there's two materials together. They're being stretched or squeezed, and because they're held together, okay, it says there the changing length in A will be equal to the changing length in B. Does it make sense? Okay. The changing length in the one material is equal to the changing length in the other material. Right, and remember, if we cast back to the previous lecture, changing length was given by delta L. Okay, I made it a small l, a big L is okay, it's the same thing. So delta L of the one material is equal to delta L of the other material. Delta L A is equal to delta L B. Also, the strain, okay, because they are changing shape by the same amount, the strain in A is equal to the strain in B. And of course, the symbol for strain, sorry, hang on, just give me a second, sorry. I'm sorry about that, just slight diversion there. Oh, where were we? Right, I was saying that, so the change of length in material A is equal to the change in length B, and in symbols, delta LA is equal to delta LB. And also, because they're all acting together as a single unit, strain A is equal to strain B, and then in symbol terms, epsilon A is equal to epsilon B, or strain in A is equal to strain in B. But we know that, remember, Young's modulus, now f here, little f, is also a symbol used in engineering and science for stress, but I'm going to keep using the small sigma, okay? So if it's f or small sigma, it means the same thing, okay? But we know also that E is equal to stress over strain, okay? And if you make strain the subject of the formula, then strain is equal to stress divided by Young's modulus, okay? But we said there that the strain in A is equal to the strain in B. Therefore, we can deduce that from here, the strain, the stress in A divided by the Young's modulus in A is equal to the strain in, is equal to the stress in material B divided by E of material B. Okay, once we equate this to each other and rearrange it, it comes to that there. So then we can see it there. And that there is called the modular ratio equation, which I'm going to rewrite for us again quickly. I'm going to say that there. So it comes like this. Let me just take this out here, like so. Right, so therefore the stress in material A over the stress in material B is equal to Young's modulus of material A divided by Young's modulus of material B. If you rearrange all of that, okay? If you rearrange all of that over there, it's going to be stress of A over stress of B is equal to E of A over E of B, okay? And that there is equal to M. And M is known as the modular ratio. Modular ratio. Okay. And for concrete, like we know it, concrete, M is normally in the vicinity of 15. Okay, so the modular ratio for concrete is 15. That means if we take Young modulus of steel divided by Young modulus of concrete, it's around 15. It's 14.3, 14.4, 15.1, but it's generally 15. Okay, so that's known as the modular ratio equation. Right, we're going on. I'm going to the next page. Then secondly, it says there, since the load carried by material A plus the load carried by material B, that there is equal to the total load. Okay, so the total load is shared by both materials. Okay, now remember, if you think of a concrete column with steel bars in it, okay, even though they're all carrying, the load is being shared by both of them, the load carried inside of each of them is not the same. Okay, they shorten or lengthen by the same, they share the load together, but they don't carry the same amount of load inside the materials themselves. Okay, so if you look at that closely there, the force, the load carried by A plus the load carried by B is the total load F. Okay, and of course, if you remember the formula here, if we look at this, stress generally is equal to force over area. Remember that? Okay, so if you make F the subject of the formula, F is equal to stress multiplied by the area. And if I go back to the page I'm coming from there, okay, the force in A is equal to the stress in A multiplied by the area in A, the cross-section area, plus the stress in material B multiplied by the cross-section area of material B is equal to the total load. Okay, I know that's a bit of a mouthful, people, but that's actually only the two big equations you need to know in this section. Okay, so if I rewrite it, so from there, so the stress in A times the area of A plus the stress in material B times the area in material B is equal to the total load. I'm going to call this I'm going to call it T there for total. Okay, so people, that's the two equations we need to remember for this part of it. Okay, and I'm going to put a nice big fat rectangle around it like so. And the other one is that over there. Okay, right. So just to recap, stress of A over stress of B is equal to E of A over E of B is equal to M. That's the modular ratio equation, and for concrete it's generally in the region of 15. And notice it's a ratio, it has no units of measurements. Why? Because we're taking, what's the unit of measurement for Young's modulus? Is newtons per millimeter squared, and newton per millimeter squared divided by newton per millimeter squared is equal to a number, it's a ratio. Okay, and of course the total load, okay, the load carried by A plus the load carried by B is equal to the total load carried by the whole structure. Okay, but of course from this formula here, okay, if we make F the subject of the formula, okay, F is equal to stress times area, which is that over there. So the stress in A times the area of A plus the stress in B times the area of B is equal to the total load. So that's the two formula we're going to need to know for this particular section. Okay, right, let me clean the board off and let's do one or two examples and see how they work. Right, there's our first example there. A reinforced concrete column is 3 meters high and has a cross section of that, so it's square, 375 square. It is reinforced with 4 by 25 millimeter bars, symmetrically placed steel rods bars. Okay, the column carries an axial load of 600 kilonewtons. Right, I'm going to draw a little picture to see what that all looks like. Right, so I think I'll draw it over here somewhere. So there's a column. I think I'll rather move that to the side, I think, rather. Okay, people, I'll move that sketch to the side there. There's a little picture. A concrete column 3 meters high. It is 375 square. It's got 4 bars placed symmetrically. That means they sort of place at equal spaces. They normally place in the corners. Okay, they be put at the corners there. And they're all diameter 25 millimeter bars. The column carries an axial load of 600 kilonewtons. So that's F. So that's L. That's F. That will give us the area. Okay. The question says determine the stress in the steel and the concrete. Number 2, determine the shortening in the column. Alright, let's see. Let's say number A. I'll do it over here. Right, so I'm going to state the formula. So we know that the stress in the steel over the stress in the concrete is equal to E of the same material over E over concrete. Okay. I'm just stating this formula over here. Where is it now? Well, yeah, you know it is. I'm just stating that equation there, okay, that I wrote earlier. Right, I'm just stating that equation there, okay. Right, a little different, but it's the same thing, is equal to M, modular ratio, okay. Right, and we don't know what this is, but do we know what this is? Yes, we do. It says there, the E for steel is 207 gigapascals divided by E for concrete 13.8 kilopascals. Now notice there, maybe I should just make a note here. Right, we did this in conversions in applied mechanics. Okay, 207 gigapascals is equal to 207 times 10 to the power 9 pascals. And what's pascals? Pascals is newtons per meter squared. Okay, and of course if you convert that to millimeters squared, we divide by 1,000 squared, and that gives us 207,000 newtons per millimeter squared. Okay, so if we convert gigapascals to newtons per millimeter squared, in effect we just multiply by 1,000. We did this in the applied mechanics conversion. Okay, but I can do it here, but I didn't do it here. Why not? Because I'm dividing exactly the same units by each other. Okay, so I can convert both to 1,000, or I can leave it like this. I'll get the same answer, right? So let's see what M is. M is equal to 207 divided by 13.8, and it's equal to exactly 15. Right, exactly 15. Okay, let me just clean the board a bit. Right, now if I look at this here, I mean, I can also say that the stress in the steel divided by the stress in the concrete is equal to that over there. It's equal to all of that, 15. So therefore, I'm trying to squeeze in space here, okay? Notice I'm not saying it's equal to, okay? Therefore, if I do a bit of algebraic manipulation, stress in steel is equal to 15 multiplied by stress in concrete. Okay, I just made the stress in steel the subject of the formula. Now just by the way, notice here, this little statement here, it says the stress in the steel is equal to 15 times that there. So what can we say? We can say that the stress in the steel is normally about 15 times that bigger than in concrete. Okay, so the steel can take a pretty big punch. Right, so I'm now going to state my other equation, and my other equation looks like such. Okay, so it will be the stress in concrete multiplied by the area in concrete plus my stress in steel multiplied by the area of steel is equal to the total load given there, which is that over there. Okay, now let's look at this here. Do I know what that is? No, I don't. We want to find that. Do I know what this is? I can now write this in terms of that. Can I work at the area of the steel and the area of the concrete? Yes, we can. Let's do that quickly. I'm going to make this in red. Right, area steel is equal to 4y25 bar. So it's 4 multiplied by quarter pi times diameter squared is equal to, just work it out quickly. It is 1963. It is 1963.50 millimeters squared. Okay. Can we work at the area of concrete? Yes, we can. How do we do that? It's the total square bit minus the one we just found there. So it's 375 squared. 375 squared minus 1963.50, and that is equal to, so I'll say minus, it is 138, it is 138, 661.50. Come on. Right, so area steel is 160.5 square millimeters. Area concrete is 375 squared minus that is 138, 61.5 square millimeters. Okay, right, now if I look at this equation here, I mean, I've worked that out, that I know, that over there, and I can write this here in terms of that. So let's do that and see what it looks like, how it pans out. Just make it a bit smaller quickly here. Right. So let's see. So my stress in concrete multiplied by area of concrete is 138,661.50 plus stress in steel. Now remember, I'm going to write this in terms of that. So that there is equal to 15 times that over there, multiplied by area of steel, 1963.50, 1963.50. Is equal to the total load acting. And remember, people, I said in the previous lesson, convert all to newtons and everything to millimeters or millimeters squared. So that's 600,000. 600,000. Here we go. So that's 600,000 newtons. Okay. Right, people, notice there, we got one equation, we got one unknown there, therefore we can solve for the stress in the concrete. And that will answer our first question up there. Right, so stop the video here, do the calculation, do the algebra correctly, and see that you get the same answer that I do. And what did you get for the stress in concrete? The stress in concrete is equal to, I got it to be, what did I get? I got it as 3.57. 3.57. And what is the unit of measurement for stress? It is newtons per millimeter squared. Okay. Right. The question says determine the stress in the steel and the concrete. We found the one for concrete. So if that is 3.57 and the stress in steel will be equal to 15 times the one we just found. So I'm going to say times 15 and I get 53.54. So therefore the stress in the steel is equal to 53.54 newtons per millimeter squared. Okay, so we answered the first part there, the stress in the steel and the concrete. Are we done? No, we need to work out the shortening of the column. Now remember, the column will shorten, but the steel is stronger, concrete is less stronger, so we have to work them together. Okay, it will shorten by, but they're working together when they shorten. Okay, so let me just clean the board and we'll just punch out the last part of that question. Right, people, we know from the previous part A, we know that shortening delta L is equal to the load times L over the area over E. But this here is for single materials only. Okay, remember the materials are acting together. So I'm going to consider, so for this particular part of the problem, you can either consider the shortening in the steel, or, did you get the word, or the shortening in the column. Okay, you can do one or the other. I'm going to do both, and because I'm going to do both of them, and because the steel and the concrete is acting as a unit, they're going to have to shorten by the same amount. Okay, so let's just see. So that there is the shortening. Okay, the shortening in the concrete, and I want the area of concrete, and I want E for concrete. Okay, and of course here the stress. Remember, the stresses in the concrete and the steel is not the same. So if I rewrite this, okay, I'll put this. So sorry, I didn't mean that. Okay, this bit here. Okay, this F over A, is that not equal to the stress? Stress is equal to force over area. So I'm going to rewrite this looking like this. So I'm going to say the stress in the concrete multiplied by the total length over the E for concrete. Okay. And that's equal to, what's the stress in concrete? We just worked it out. The stress in concrete is 3.57. it's 3.57 multiplied by the length, which is 3000, remember, converting to millimeters, and I divide that by the E for concrete. Now I need to convert it to Newton per millimeter squared by multiplying by 1000, as I said, and it's 13800. 13800. And you work at the answer, and you check that you get the same answer that I do. And the answer I get here is 0.78 millimeters. And as I said in the previous lessons, delta L can't be a big number. If you get a big number, you made a mistake. Okay. Now people, as I just said a few minutes ago, you can either use your shortening for the steel or for the concrete to find the answer here. But for this case, just to show you, because the steel and the concrete is acting as a single unit, they should actually both shorten by the same amount. So I'm going to say or. Okay, or. I'm going to do the shortening in steel. So I'm going to say delta L in steel is equal to the stress in the steel, which we just calculated previously, multiplied by L over the E for steel. Okay. So the stress in steel we found to be 53.54. 53.54 multiplied by the length, which is the same for both of them in millimeters, divided by the E for steel, which is 207,000. And you do your calculation and you check, and what did I get? You get just give me a second. And yes, I got the same answer, 0.78. Ahmed. I'm going outside the boundaries of this thing. 0.78 millimeters. Okay, so I'll say it again. You can either calculate the shortening in the one material, the concrete, or you can calculate the shortening in the steel, but in this case I did both of them just to prove that these two are acting as a single unit. Therefore the shortening in both of them must be the same. When you do the calculation in class or an exam, just do one of them, but I normally do both just to check that they are the same. Okay people, so that's our first example of compound bar theory. It's called compound bar theory, where we apply the equilibrium equation and the modular ratio equation to find the stress in the steel and the concrete, and also work at the shortening of the column. Okay, I think I'll do another example, but I'll do it in the next video. I'll see you in the next video.